Hello and welcome to this video on Rust programming. In this video, we will explore more operators like Boolean operators and equality condition operators, less than greater than operators, and left shift, right shift operators. So to start with, there are several kinds of Boolean gates. One is the AND gate, then we have OR gate, then we have XOR or XOR gate, and then using these gates we can construct, and then there is not one. Using these gates we can construct NAND and NOR gate. So I have printed the truth table of AND gate here and OR gate and then XOR gate. So if you do AND of 2 bits and both are 0, then it will be 0. That is, AND gate is true only if both inputs are 1, otherwise it will be 0. OR gate, the output will be 0 when both the inputs are 0, otherwise OR will be 1. XOR gate or XOR gate will be 0 if both are same and 1 if both are different. So if you want to compute NAND gate, which is a negation of A and B, for example, we can say NAND of A and B, this will be NAND gate. So NAND gate, if you consider, then this will be 1 and rest will be 0. Oh, this will also be 1, not rest will be 0. That would be NOR gate. 1 and this would be 0. So this is NAND gate. Okay. And this NOT just flips the bit. Okay. It is a NOT gate. It computes the opposite bits of the given number. For example, if a number is x is equal to 0, which is of type say I32, then if you do not x, that means all bits are 1, which will give us -1. So that's what NOT gate is. It flips all the bits of the given number. Now NOR gate, you can write like not A or B. So this will be 1 if both are 0, otherwise it will be 0 for all other cases. So this is NOR gate. Now there is not an equivalent not XOR gate, but you can compute it if you need it. Okay. Now let's look at our program. So in this case, 4 and 2 would be 0 because 4 is 100 and 2 is 0, 1, 0. So all the bits prior to this will be 0, for example. Okay. Now if you AND this, then this 1 and this 0 will become 0, and this 1 and 0 will become 0, and all other 0 and 0s will become 0. So 4 and 2 would be 0. But if you OR, then this bit, the third bit will become 1 and second bit will become 1, making it 6, 1, 1, 0. So if you OR, it will be 6. As I said, if you take NOT of 0, it is -1. If you treat as U32, then it will give you the value of unsigned 32 max. Similarly, XOR gate, when the bits are same, it will be 0. If you OR two numbers and then take negation of that, it will be 0. So it's the same thing. Both are same. So I should probably remove one line here. We don't need this. You can't perform bitwise operation on floating points. This will give you an error. It won't compile. Similarly, we can have equality operators. Now, equality operators result in Boolean values. There are two Boolean values, true and false, and you can compare true and false with only true and false. You cannot compare that with a number. For example, in C or C++, 0 is false, while all other integers are true. But that won't happen in Rust. You can't compare a number with true or false. True or false are result of Boolean expressions. So this is a Boolean expression, 10 is equal to 10, so which will be true. And that's why other will pass. 10 not equal to 9 is another Boolean condition. This is not equal to operator. So it will also result true. Now you can combine Boolean operations. For example, here I have combined two Boolean operations, equality and not equal, with AND gate. This is logical AND. It does not do bitwise operation. If the result of two operations are true, then it will be true, otherwise false. Also note that from recall from floating point number discussion, you should avoid comparing floats for equality because of the storage scheme defined for floating points in triple E 754, 0.3 may not be equal to 0.1 and 0.2. Sometimes it varies. Okay, so you should not compare this. For example, 0.4 will be equal to, no, 0.4 will also not be equal to. 1 would be equal to 0.5 and 0.5. This will work. This will be equality operator, but it won't work otherwise. And you have to treat them as floating point numbers. You can't say 1, you have to say 1.0. Similarly, booleans you can compare. False or true will be true, true and logical AND will be true. Two pipes means logical OR, not bitwise OR. And two AND means logical AND, not bitwise AND. So we can combine this OR to see here. The first condition is false, true, and the second condition is false. In this case, short circuit evaluation will happen. That means if any condition is found true, rest will be not evaluated. So after evaluating this, the 10 is equal to 9 does not need to be evaluated because this true alone will make the entire statement true. Similarly, for AND, false condition is the short circuit of the circuit. I mean Boolean expression. So 10 is equal to 9 if it would be first comparison in expression, then 10 is equal to 10 will not be evaluated if placed at the second position. Similarly, you see that this is a NAND gate construction, this is a NOR gate construction because we have a NOT operator in the beginning. Then we have shift operators. You can left shift this 2 less than 2 means shift 2 by 2 bits. So this will be equal to 2 into 2 to the power 2, that is 8. And right shift up is like division by 2. So if you say, for example, assert 8 right shift twice, that will be equal to 2. This operation is reverse of this operation. But note that -1, if you try to right shift, it will yield -1. The reason lies in the fact that -1 is all ones, when the most significant bit is 1. Now if you want to shift, these 7 bits have to be shifted. Okay, but that won't give you minus 0. If you shift these bits, then it won't give you 0. That is why -1 when right shifted, it always gives -1. So let's see this program in action and see if any of our assertions are wrong. Delete this. So you see all assertions are true. So instead of these numbers, you can use variable names of appropriate type and these operations will work. This more or less covers almost all of the most common operators which you will use in programming. There will be some extra operators like that 2 plus is equal to 2 is equal to 4. This should work. I have not tested this, but no, it won't work. So you cannot assign to expressions. Okay. So you can't use this like plain values. You have to evaluate the plus is equal to operator. So for example, x is equal to 2. We let x is equal to 2 and we can say that x plus is equal to 2. And then if we say assert x is equal to 4, this will work. Okay, this is not mutable, so it won't work. This should be mutable. Yeah, now this should work. So we run this again and no assertions are false. That means x has become 4. So there is plus is equal to operator, there is minus is equal to operator, there is division slash is equal to operator. They operate in the same way. There is ampersand is equal to operator, and so on. We will see more operators when we write more code, but this more or less covers most useful operators which we'll deal with. With this, we come to the end of this video. In the next video onwards, we will start writing small programs so that we can learn from them. For example, next program, I'm going to introduce the concept of variables and how to name them, identifiers, and how we can use those variables to write small programs so that we can learn by writing some code and practice. It will be good practice to write those small programs so that the theory which I'm talking about till now comes into practice and those are reinforced. So if you have liked this video and found it useful, then please subscribe to the channel and like the video, and don't forget to share it on social media so that it can reach many more students like you and they can benefit from this Rust programming tutorials. And if you have a comment or a suggestion, or you want to say something, then please make use of the comment box and let me know your opinion. And with that, I will end this video. Thanks a lot for watching. Happy programming.